Okay, so again, this is a systems modeling lecture, which is part of the concept exploration phase of the system engineering life cycle. So far, we have talked about the first two phases in detail, and we started with the need analysis. Now we're looking at the concept exploration. After the next lecture, this one and the following, then we're going to transition to the concept definition phase. But before we get to that point, let's talk about the agenda for this morning. We are going to discuss basically, as I did already, discuss the summary of what we did last lecture, in which we spent some time discussing what are sets, relations, and functions. And then you're going to see how those topics are connected to what we're going to discuss this morning. But before we get to that point, we're going to discuss what's modeling and what's going on. So this is a recap of a general summary of what we did last time. In our previous lecture, we discussed what were functions, and we also discussed that the functions were a subset of the relations, and the relations were a subset of the sets. So we went into the definition, reviewed the definition of sets, and some of the operations that are used to build these relations, and how those relations can be used to build these functions. Functions are going to be our tools to build these simulation models that we need for representing the behavior of our systems. So we will use these three mathematical concepts to describe the structure and behavior of system models. We will focus on the functional system architectures, and we will represent the function of the system using these relations and or functions. So what is modeling? I'm pretty sure that you have heard about this word before, especially in some of your other courses. Modeling is to model a phenomenon is to select from a set of models on the basis of predefined criteria, an element to represent that phenomenon. So models are, it depends on what type of subject you're studying. You can mention different type of models that are used in that particular subject. For example, in biology, there's models. In physics, there are models. In industrial engineering, we also have our own type of model. So we are going to choose what will be the best strategy to represent our system or our subsystems within the system. Modeling is the essence of system design. So that's why we're spending so much time on this particular subject. A familiar example of modeling is linear regression. So you're familiar with linear regression. We're basically using set of models in the set of equations of the form y equals ax plus b, where a and b are real numbers. And most of the time what you do is you try to fit a curve to a set of data to try to forecast the behavior of whatever phenomena you're looking for. A set of data of the form x, y is modeled in this set of models by choosing a and b, such as the sum of the squares of the deviations from this line is minimized. Sometimes it is said that all models are wrong. The reason why that statement is said is because there's no model that is capable of representing 100% the behavior of a phenomenon. So most of the time when you're building these models, you are basing the representation of the system on certain assumptions, and there's multiple reasons for that. most of the time is because the lack of resources. Maybe you don't have enough time, so you have to make some assumptions to facilitate the development of such models. In terms of systems engineering, models for systems engineering include the following: physical models, prototypes, drawings, specifications. It depends on what level of the system hierarchy you are. I will say at the bottom level, when you're looking at parts, most likely you're looking at drawings, making sure that those parts are designed as expected. But when you get at the top level of the hierarchy process, then you're looking at the behavior, how the integration of this subsystem. So you want to know more about the behavior of the combination of components. So at that level, you might be looking at models such as discrete event simulation, in which you are providing an input to your system and you want to know what is the behavior in terms of the output of the model in this case. Mathematical models based on physics, traditionally produced by engineers. So there's discrete event systems and multiple other type of models that can be used in that sense. System theoretic models, these are better suited to describe and manipulate organization problems, such as discrete time automata, discrete time models or state machines, and discrete event models. In this course, we will concentrate on the system theoretic models, which are the second group. We are not going to look at physical models, but we are going to focus on these system theoretic models, whose underlying theory is the set theory that we discussed in our previous lecture. So the concept of a dynamical system. Dynamical system theory is an area of mathematics used to describe the behavior of a complex dynamical systems, usually by employing differential equations or different equations. So in this particular class, we are not going to go into differential equations, but we are going to look at some difference equations. When the time is modeled as a continuous, like if you're considering not only 1, 2, 3, but you're also looking at fractional time, those are continuous models. So differential equations are employed, and the theory is called continuous dynamical systems. These type of models are used frequently in electrical engineering, in which you're dealing with changing current, voltage, and so on. When time is modeled as a discrete, the difference equations are employed. The theory is called discrete dynamical systems. The theory deals with the long-term behavior of dynamical systems and the solutions to the equations of motion of systems that are primarily mechanical in nature. Many situations in applied science can be modeled by dynamic equations. Dynamic refers to phenomena that produces time-changing patterns. So again, we are going to be providing some type of input throughout time, and we want to know what is the behavior of the system based on that input. So if the time scale is assumed to be continuous, the direction of the change of the characteristics is described by differential equations. As I mentioned, when the time scale is assumed to be discrete, we are looking at time periods that are integer values. So we're going to look at 1, 2, 3, and so on. These are modeled using difference equations. So in dynamic systems theory, the system characteristics are usually divided in 3 classes. And this is very important. 3 classes are the following. The input of the system, the internal variable that summarizes the state of the system, and the output. So we are basically representing the behavior of a system by looking at what is coming in, how is that affecting my behavior, and then if that is generating some type of output. Most of the time we use, this is a simple way of representing a system model. This is what we usually call a black box model, in which you have a box and you don't know what's going on inside. The only thing you know is there's some type of state. So if we think about open systems, for instance, we can have something like a traffic light in which there are colors Colors mean something for the vehicle. So most of the time what you have in these systems are some type of sensors. It could be on the road, or it could be cameras on top of the light, or the traffic lights. And according to the input that you're receiving, then you're going to make some change in your state. So for instance, if this area is green, or this light is green, if you notice that there are cars on the other direction, that is going to be captured by the sensor, and that's going to trigger a change in the state of this system. That is going to tell, oh, you know, there's people waiting in this row, so you have to change this green light to red, and you have to change this one to green at some point. So the input is the data that is gathered by the sensor. The state is the current state of the system. So let's say this is green right now. There's input saying that there's cars waiting. So now we're going to trigger a change. So this has to go from green to red. And the output is going to be that change in light. So very simple, right? That's the type of behavior that we want to capture. So if I give you this input and this is your state, is that input triggering a change in your state? If that's the case, then are you going to generate an output based on that? So from here, let me stop here. We're going to go to the next part. So let me stop this.